equation of output equation of DC machine. Let us talk regarding D and L of your output, D and L of your DC machine. See here, the output equation of DC machine, I am going to derive later. The output equation of DC machine will be in terms of a product D square. As you see in a synchronous machine or induction machine, the output can be also can be derived in the terms of what D square product, where the D square product represent what? Represent the size and volume of the machine, or we can say that the size or volume of the active iron parts of the machine. Where D is something but what? D is nothing but your circumference of your armature with respect to DC machine, and L is nothing but length of the armature. So if D square L represent what? Represent the size and volume of the iron parts of the machine. So what are the basis aspects of the design? So good design is that you have to get the maximum output. You have to get the maximum output with the less with the D square L product. With the D square L product would be as less. Means if you take D square L product, it should be less. If it is less means what? Definitely it will be a small machine. So the machine should be small enough, and you have to get the maximum output. And then that type of machine is considered as a good design, because small in size means what? Even the cost of the machine will be reduced. So with most economically, you are going to get the maximum output. And what is the condition? You have to maintain that D square L product is small. Okay. And that's the thing. And regarding peripheral speed, everyone knows the peripheral speed influences the value of the machine diameter. Means once again, the speed depends upon the circumference of your armature. Once again, it's given by V is equal to pi dn. The usual value of range is between 15 to 50 meter per second. Our design limit of peripheral speed is around 30 meter per second. Okay. Means usual design it is between 15 to 50 meter per second. Normally it will take around 30 meter per second for the design. Next, third case come regarding L by tau ratio. L by tau ratio, you can see here L by tau ratio. You can see this is nothing but your pole. You can see here is a pole core and nothing but your pole shoe. Okay, it's nothing but B. You can see here B is something about your pole arc, and BP is something about your width of the pole body. BP is something about the width of the pole body, and L is something about the core length of the pole. Core length of the pole is also equal to the length of your armature. So whatever the length of the pole core will be equal to the length of your armature. Okay, that will be same. Length of pole core and length of your armature also will be almost same. Okay, now. Ratio of L by tau is a prime factor to decide the length of the core and the proportion of the pole. As you know, everyone, we are going to use this L by tau ratio. So pole can be taken either two types. It may be either circular or it may be a rectangular. Okay. Pole cross section, that is circular or rectangular, is guiding factor to control the mean length and weight of the cost of the copper in case of field winding. So with respect to the field, either I can go for circular pole or either I can go for a rectangular pole. Once again, if I go for circular pole means the mean, then you have to do the what? You have to do the winding on the pole. Winding on the pole, that is something about your field winding. So if you go for circular pole, definitely the length of meter of the winding will be less. Or if you go for rectangular pole, the length of meter will be more. Okay. So rectangular pole cross section contributes a larger meter length and weight of the copper. So if you go for circular pole, the length of meter of your winding will be less and the copper will be less. If you go for rectangular pole, the length of meter will be more and definitely weight of the copper will be more. So at the same time, you select to use the laminated structure which reduces the production cost. So it depends. Which type of rating of the machine. Based on that, you're going to decide which type of pole, whether you go for a circular pole or you go for a rectangular pole. For a given flux and the cross section, the length of meter of field winding is minimum when the periphery is square and the length of pole is approximately equal to pole arc. So what's the meaning exact? What is the meaning? Exact meaning of this sentence is for a given flux on the cross section, the length of mean term of field winding is minimum when the periphery is square and the length of pole is approximately equal to pole arc. Length of pole is exactly equal to pole arc. So if you want the minimum length of minter, then what have to go? Then what have to do means either you can't go for a circular pole or either you can't for a rectangular pole. I try to go for a square pole. Square pole means what? This pole arc. And this pole arc will be equal to what? Equal to the length of the your pole core. The pole arc is equal to the length of the pole core. Then exactly it will become a almost square. Okay. Then the length of minter of your winding will be minimum. Okay. Okay. Seeing with respect to this figure, we can see BP is something about the width of the pole body. It will be in meter, and then B is equal to pole arc, and tau is equal to pole pitch. This is something but B is equal to a pole arc. Once again, everyone knows tau is equal to a pole pitch by D by P, and psi is very much important one. Psi is something but what? Pole arc to pole pitch. Polar to pole pitch. What is polar here? Polar is something about your B, and what is pole pitch? Pole pitch is something about your tau. And usually the psi, polar to pole pitch, the ratio of polar to pole pitch lies between 0.64 to 0.72. Okay, 0.72. As I told, if I go for a circular, not circular, square cross section. Square cross section of the pole, then what will happen? This pole arc will be equal to what? Equal to L of the pole core. In that case, what will happen? For L is equal to, then what will happen? For L is equal to B, means what? The length of pole core is equal to the length of pole arc. Then what will happen? L is equal to B. Then substitute for B here. What is B here? Psi into tau. We know that psi is equal to B by tau. If you go for once again a square pole, then L is equal to B, means the length of pole core is equal to a length of pole arc. Then substitute for B here, B is something but what? Psi into tau. For this equation, I'm going to use in the problem. Psi into tau. The ratio of L by tau also lies between 0.64 to 0.72. Once again, this L by tau also varies between whether you go for circular poles or you go for square poles like that. Okay. Practically, length of core is taken slightly higher. Length of core is slightly taken higher, so that L by tau lies between 0.7 to 0.9. L by tau lies between 0.7 to 0.9. Okay, these are a little bit of theory aspects regarding the L by tau ratio. Okay, let us with this. Let us go for the output equation of DC machine. A simple expression. Let us derive the output equation of a DC machine. The output equation of a rotating machine is a mathematical expression that relates the main dimension, specific magnetic loading, and specific electrical loading. The main dimension means nothing but T and L will be related to what? A specific magnetic loading and specific electrical loading and speed. These are the parameters. Let PA is something about what? Power developed by the armature. Okay, power developed by the armature. Definitely, if you take either a DC machine, it may be operated. It can be operated as a generator or it can be operated as a motor. Definitely, where you take the output will be taken across the armature. So PA is equal to power developed by the armature in kilowatt. E generated EMF. Definitely with respect to the armature generated EMF. Then IA armature conductor. Okay. Current in the armature current in the armature. Okay, armature conductor. Then just write current here. Current in the armature conductor. IZ current in each conductor. Okay, IZ represent current in each conductor. This IA represent what? Current in the armature conductor. Total armature conductor. Then N is equal to machine speed in RPS, and A is equal to number of parallel path, and P is equal to number of poles. And PA is equal to specific magnetic loadings. AC is something but specific electrical loadings. Z is equal to number of conductor. D is equal to armature diameter, and L is equal to armature core length, and C naught is equal to output coefficient. L is equal to armature core length. Also, this L is equal to what? Also, it will be equal to the length of the pole core. The length of the pole core will be equal to the length of the armature. Okay, these are some parameters. Let us derive. Power developed by the armature. Power developed by the armature in kilowatt. PA is equal to what? Generated EMF into armature current in 10 power minus 3 taken kilowatt. So generated EMF in the armature will be E into armature current IA into 10 power minus 3. And generated EMF is given by the formula 5ZNP by 60A. EMF formula for generator 5ZNP by 60A, where A is something about number of parallel path. This is N. This is N will be what? N will be RPM converted into RPS. So N is equal to what? N divided by 60. Then this will be converted into RPS. Where this N is something about a machine speed. Don't write synchronous speed. It's a DC machine. Write a machine speed. Okay. So 5ZNP divided by A. So circuit for N here. N is nothing but what? 60 into N. 60 into N means 60 get cancelled. What remains here? Only N remains. So 5Z NP by A into IA into 10 power minus 3. Okay. Now, just rearrange this term. 5P, then IA by A into Z into N into 10 power minus 3. I am just rearranging these terms. So 5P into, so IA by A can be written as IZ. IZ is something about what? IZ is something about the current in each conductor. Okay. IA is something about the current in the armature conductors, our total armature conductors, divided by A is something about parallel path. If divided by parallel path means what will get? The current in each conductor. Okay. 5P into IZ by Z into N into 10 power minus 3. So what is 5P? So 5P means, you know the expression for BAB. BAB is equal to 5P by pi dl. And you know for expression for specific electrical loading, AC is equal to what? IZ into Z divided by pi d. Using that relation, I am going to use. So 5P can be written as what? Pi dl by BAB. And IZ into Z can be written as what? Pi d into AC. Because BAB is equal to P5 by pi dl. And AC is nothing but what? IZ into Z divided by pi d. Using that normal formula of specific electrical loading and specific magnetic loading, you can write, you can substitute for what? 5P and IZ into Z. To substitute here, pi dl into BAB into pi d into AC into N into 10 power minus 3. Just multiply here. Pi square BAB AC into 10 power minus 3 into T square LN. Okay, T square L into N. So this term, this entire term is called as what? C0, where C0 is something but what? C0 is something but your output coefficient. Given by the formula pi square BAB AC into 10 power minus 3. And D is something but the diameter of your armature, and L is something but nothing but the length of the armature. Okay. So okay, now this is your what? This is nothing but what? PA means PA is something but what? Power developed by armature. Power developed by armature is given by what? C0 D square Ln, where C0 is the output coefficient. Sometimes the value of maximum gap flux density BG is specified instead of the value of average flux density. The expression C0 has to be modified in that case. Sometimes instead of BAB, they'll give in terms of maximum gap flux density. Means they'll give in terms of BG. Then the C0 will be modified. What is now? BG is something but what? BG is something but everyone knows. BG is equal to what? BAB by psi. BAB is nothing but your average gap flux density, and psi is nothing but what? The ratio of polar to pole pitch. And psi is also written in the form, also written in Kf, where Kf is nothing but what? Field form factor. Okay. Field form factor that is equal to psi, that is equal to what? Polar to pole pitch. So sometimes it will express in terms of, instead of BAB, it will be expressed in terms of BG. Then your output coefficient C0 will be modified. So what will become C0 now? C0 is equal to pi square. So substitute for BAB here. So BAB is nothing but what? Your BG into psi. So BG into psi or BG into Kf. Either way you can write it. So C0 is equal to pi square BG into psi AC into 10 power minus 3. This is what? This is your output equation of a DC machine. A simple one, not too much long. It will be easier one. Okay, go through it. This is the output equation of a DC machine. So based on this output equation, let us solve some simple problems on D and L. On D and L. Let us continue. We take first problem. Here, a 5 kilowatt, 250 volt, 4-pole, 1500 RPM shunt generator is designed to have square pole phase. Means square pole phase. In square pole phase means definitely the pole arc P will be equal to L. P is equal to L. Square pole phase The loadings are the average flux density in the gateway is 0.42 Weber per meter square and ampere conductors per meter. Nothing but AC, 15,000. Find the main dimensions of the machine. Assume full load efficiency is equal to 0.87 and ratio of a pole arc to pole pitch is equal to 0.66. A simple problem. Finally, what you have to find out? You have to find out D and L of your armature. So, if you see here, this is nothing but your Shunt generator. So, if everyone knows that Shunt generator is driven by a prime mover. So, any generator is driven by a prime mover. Since it is DC, normally it can be driven by either by your either by any hydro or Pelton wheel or any hydro. With respect to hydro, I can use either any Pelton wheel or Francis turbine, or I can use any IC engines, or I can use any steam engines to drive what? To drive the generator. Okay, so to drive the generator. Now, let us see now. Power developed by the armature of a generator. Power developed by the armature of a generator, PA is equal to what? Input power minus rotational losses. Means in general, if you take as a in general, you can take all the losses. I written here rotational losses, but you can take all the losses. So for generator, what you are going to what? You are going to do the input power. Input power means what? Input power is nothing but the power given from the turbine. Okay, or power given by your prime mover. So total input power will be what? Input power is equal to what? Output power of your armature plus rotational losses. If you write input power is equal to what? Your output power developed by the armature plus losses. Input power is something but what? Input power is nothing but given by your turbine. Okay. Here simplicity I have taken as rotational losses. If you want, you can take all the losses, because in this problem they're not specified regarding all type of losses. Just I have taken for the equation case I have taken here losses. So input power is equal to what? The power developed by the armature plus losses, or the power developed by the armature for a generator PA is equal to what? Input power minus rotational losses. What is input power? I say input power can be written as what? Output power by efficiency, because they are given here data regarding the efficiency. Output power by efficiency minus rotational losses. So nothing is given regarding any losses in this problem. So what is rotational losses? Is nothing but your constant loss, like friction, windage, and iron loss. These are all called as a constant loss. In case of large machine, a very small difference between your input power and PA. What you going to input power from the turbine and what is the power developed from the armature almost remain same, because losses will be negligible for large machines. So the friction, windage, and iron loss could be neglected. Means this rotational loss can be neglected, but we can't neglect this the variable loss. What is variable loss? Variable loss is nothing but your copper loss. Copper loss you can't neglect, but rotational losses you can neglect with respect to what? With respect to large machine. So don't worry about these losses, because nothing is given in this problem regarding the losses. So we will stick on to this formula. Power developed by the armature for generator PA is nothing but what? Output power by efficiency. This is for your understanding. I given the Shunt generator. This is everyone has already learned this one, Shunt generator, and these are some of the equations. Equation regarding the Shunt generator. Okay, just to go to that one. Now, power generated by the armature is given by what? Output power by efficiency. Power generated by the armature of your generator given by what? Output power by efficiency. What is output power given in the problem here? Output power is something but 5 kilowatt. Now 5 kilowatt divided by efficiency. So if they give efficiency, definitely what we'll get indirectly what what you come to know the losses. Because efficiency is 0.87, definitely another 0.13 will be regarding the losses. So 5 into 10 power 3 divided by 0.87, what you got here? What you got here? 5.75. So the output of your armature, of your generator, what is this one? 5.75 kilowatt. So it includes what? It includes the output along with the losses, because efficiency is 0.87. So it includes even in this, it includes what? It includes the losses also. Okay. So PA is equal to what now? 5.75 kilowatt. Next. What is the machine speed? N with respect to RPS. 1500 by 60. What do you get here? 25 RPS. Then calculate what? Calculate output coefficient C naught. Pi square into PAV into AC to 10 power minus 3. Pi square into 0.42 into 15,000 into 10 power minus 3. What do you got here? 62.18. And we know that the power developed with armature PA is equal to what? C naught D square Ln. Then I want what? I want D square L. So D square L is equal to what? PA divided by C naught into N. So you know now PA. Power developed by the armature. Power developed by the armature given by what? 5.75. Power developed by the armature given by what? 5.75 divided by 62.18 into 25. Okay. So here you can see a power developed by armature is what? 5.75. It includes what? It includes along with the, because the efficiency is given. If efficiency is given, then definitely there will be a losses. The final output of your armature will definitely include the losses. 5.75 divided by what? 62.18 into 25. So if you see here in the problem what is given? The 5 kilowatt means originally the output of the machine will be what? 5 kilowatt means 5 kilowatt you are going to get it. But the output of the armature includes this 5 kilowatt plus losses. Okay, 5 kilowatt plus losses. Finally, the output of the machine, what you get, 5 kilowatt. Okay. So PA is nothing but output power of the armature. Just you don't confuse here. The output power of the armature includes the output of the machine plus losses. Finally, the output of the machine will go. The output of the machine is 5 kilowatt, but the output of the armature includes what? Includes the output plus losses. Okay, total output power of the armature plus losses. Okay. Now what do you get here? D square L is equal to what? PA divided by C naught into N. 5.75 divided by what? C naught is what? 62.18 into N. What is N here? N is equal to 25. And D square L is equal to what? 0.0037 meter cube. Take this as equation 1. As everyone knows, we did same type of problems in synchronous machines and induction motor. This is equation 1. Now, in the problem, what is it? It has given? It has given what? It has given a square pole. Square pole means what? This pole arc will be equal to L. Okay. For square pole, core length to pole arc. Core length to pole arc means L by B is equal to 1. For square pole, core length to pole arc L by B equal to 1 because both are equal. For square pole base, core length L is equal to pole arc. So L is equal to B. Then you know that psi. What is psi now? Psi is equal to pole arc to pole pitch. What is pole arc? Pole arc is nothing but B. And what is pole pitch? Pole pitch is nothing but tau. Okay. Now core length L is equal to pole arc. Core length L is equal to pole arc B. Then what is B here? B is nothing but what? Psi into tau. Psi into tau. Substitute for B here. Psi into tau. What is psi? Psi is nothing but what? The ratio of pole arc to pole pitch. The ratio of pole arc to pole pitch is given in the formula. You can see here the ratio of pole arc to pole pitch is 0.66. It is given in the problem. So psi is equal to 0.66 into tau. Okay. So 0.66 into tau, what is tau now? Pi d by P. 0.66 into pi d. Pi into d. Number of poles is given in the problem. It is nothing but 4. If you solve this one, what you get? 0.518 d. That is your equation 2. So substituting for L from equation 2 in equation 1. From 1 and 2, what you get? You can calculate D. After calculating D, you can calculate what? You can calculate L. If you take D square L, if you take D square L means what? This will be what? Still a lower value. It should be a lower value. It should be as small as possible so that the machine will be less and you can get the maximum output. Then you can consider this as a good design. Okay, this is the what? This is the solution or the solution of this problem. D and okay. Next, based on if in the problem if efficiency is given, it will be simple for you. If efficiency is given, it's a simple for you to calculate what the power developed by the armature to generator. If they not give efficiency, then you have to calculate the loss. Because if they give efficiency indirectly, you come to know the losses. Otherwise, you have to what? Otherwise, you want to calculate the losses. That's the type of problems we'll see in the later stage. Now, come for second problem. Yeah, second problem. Find the main dimension and the number of poles of find the main dimension and number of poles. Okay, here you have to calculate what extra. They're not given number of poles. You have to calculate the number of poles of 37 kilowatt, 230 volt, 1400 RPM shunt motor, so that square phase is obtained if the average gap density is 0.5 T and AC ampere conductor per meter is at 22,000. The ratio of polar to pole which is 0.7 and full load efficiency is 90%. Okay, full load efficiency is 90%. Here, what you have to find out, you have to find out a number of you have to find out the number of poles. Okay, you have to find a number of poles. I think in last class I explained the factors to be considered for selection of number of poles. Okay, in that the first factor is what the frequency. So the frequency of DC machines should lies between what? Lies between 25 to 50 hertz, because you can't because if you go on increase number of poles and frequency increase, then there will be more flux reversal, and definitely there will be more the iron losses, nothing but the eddy current loss and Hysterics loss in your armature. Taking that point into consideration, we can see that the frequency of flux reversal is given by the frequency of flux reversal. Flux reversal is given by what? F is equal to what? Pn by 2. That's the formula. For the iron loss to be less, the frequency should lie between 25 to 50 hertz. The frequency should be less between 25 to 50 hertz. Let us choose P is equal to 4. Means then try to calculate if F is equal to what? Pn divided by 2. So 4 into, okay, what is N here? Okay, what is N? So what they given? Pn by 2. Okay, here 1400 RPM. Okay, no problem. Okay, this is converted into seconds here. I have done here. See here, Pn by 2. So 4 into N. I want N. So N. Okay, N directly calculate here. This is RPM, but capital N. 1400. 1400 divided by 60. I have done here. 1400 divided by 60. I counted into seconds. Okay. 4 into 1400 divided by 60 into 2. So I have not done separately here. Machine speed. If you want to calculate, you can go for one more step. Machine speed N is equal to what? Capital N by 60. That I have done here itself. So N is equal to 1400 by 60 into 2. What you get here? 46.66 hertz. If you take P is equal to 4, let us take P is equal to 6. If I take P is equal to 6, F is equal to what? Pn by 2. Once again, 6 into 1400 divided by 60 into 2. Then what you get? 70 hertz. But the frequency should be what? Within range of what? 25 to 50 hertz. So I can't take what? I can't take the pole is equal to 6. What I can do? I can take pole is equal to 4. I can take 4 because it lies between what? 25 to 50 hertz. So if I select this frequency, means indirectly what I can say, the frequency of flux will be less, and definitely the iron loss, or constant loss in your armature will be less. So okay, with this we can take what? Choose number of poles. P is equal to 4. Okay, choose number of poles. P is equal to 4. Let us calculate that. PA is something but the power developed by the armature. PA is equal to what? Output power by efficiency. Output power is given. Output power of the motor is given 37 kilowatt. 37 divided by 0.90. Then what do you get here? What do you get? 41.11 kilowatt. 41.11 kilowatt. If efficiency is given, indirectly we'll come to know the losses also. We'll come to know the losses. Okay, 0.90. Machine speed. Okay, here I calculated here. Machine speed N is equal to 1400 by 60. What do you get here? 23.33. Same 23.33 you can put it here. Directly put it here. 1400 by 60, 23.33 RPS. Calculate output coefficient C naught, pi square VAV into AC to 10 power minus 3. Calculate C naught. What you get? 108.56. And once again, power developed by the armature is given what? C naught D square Ln. Calculate D square L. Substitute the values, and what you get here? 0.0162 meter cube. Okay, this is regarding question 1. Once again, in the problem, we see they are given what? They are given square phase. They are given square phase. So for square phase, core length by pole arc, same thing. L by B is equal to 1. For square phase, core length is equal to pole arc B. Psi is equal to pole arc by pole pitch B by tau. Core length is equal to B, nothing but psi tau. Psi tau here It is given what? It is given what? The ratio of polar to pole pitch psi is given as 0.7. 0.7 into tau. Tau is something but what? Pi d by p. 0.7 into pi d by 4. Then what you got? 0.549 d. So using equation 1 and 2, you can calculate what? You can calculate the D and L. D and L of the machine. You can calculate D and L of the machine. Okay. This is the second problem. You can see there's a difference with respect to the first problem. And in the first problem, it is a simple one. They're given the number of poles. Here, they're not given the number of poles. You have to select the number of poles such that the frequency lies between 25 to 50 years. This is a difference if you want to compare with the first problem. Okay. Now, let us go for third problem. Where in the third problem, the efficiency is not given. If efficiency is not given, then you have to calculate what? You have to calculate the then how do you going to calculate the power generated by the armature? Let us see. Now here, third problem. A design is required for 50 kilowatt, 4-pole, 600 RPM DC shunt generator. The full load terminal voltage being 220 volt. If a maximum gap density is 0.83 Weber per meter square. Say here, it has not given the average flux density. It has given what? The maximum gap density means what? It has given VG. And the armature conductor per meter is 30,000. Calculate the suitable dimension of armature core to give square pole phase. Assume full load armature voltage drop is 3% of rated voltage, and that of the field current is 1% of rated full load current. The ratio of polar to pole pitch is 0.67. A very much important problem. Same problem there as several in several question paper. Very much important problem. So here, if you go to this problem, they're not given the efficiency. If they give efficiency, directly can calculate what PA. PA is something but what? The output power divided by efficiency. Since efficiency is not given, then you have to deal this problem in a different approach and try to use all this data and try to calculate PA. You be sure that efficiency is not given, and then you have to try to calculate PA. Then how you calculate PA? Let's see. This is your what? This is nothing but your shunt generator, shunt tune generator, and these are some important relations. Everyone already learned in DC machine. These are some important relation. Okay. So I is equal to what? IL plus ISH. Shunt field current ISH is nothing but what? VSH by V divided by RSH. V is nothing but your terminal voltage given the problem. What is terminal voltage given the problem? This is 220 volt. So ISH is nothing but what? V divided by RSH. And terminal voltage V. Terminal voltage V is nothing but what? EG minus IA into RA. EG minus IA into RA. Where EG is nothing but what? V plus IA into RA. But I want terminal voltage. V is equal to EG minus IA into RA. V is given. So I can calculate what? I can calculate EG. So power developed by your armature of the shunt generator. PA is equal to what? EG into IA. And power given to the load. Power given to the load is nothing but V into IA. So IL into V, nothing but what? Power given to the load. Whatever the output coming from armature, it is given to the load. There is nothing but what? V into IA. Okay. These are some of the relations with respect to your DC shunt generator. Everyone's already learned. Learned in your previous semesters. Okay. Using this relation, let us calculate PA. What is power developed by armature? So power developed by armature PA is equal to what now? EG into IA. So I have to calculate what? EG into IA I have to calculate. Suppose if efficiency is given, then I can calculate PA is equal to what? Output power divided by efficiency. It's a simple one. Since efficiency is not given, we have to use these data and calculate PA. PA is equal to EG into IA. What is generated voltage EG? So use this relation. EG is something but what? V plus IA into RA. V plus IA into RA. V is given. What is V? V is something but the terminal voltage is given. Is nothing but 220 volt. IA into RA. IA into RA is something but what? Nothing but drop across the armature. Nothing but your drop across the armature. So if you see here, you can see here, assume that full load armature drop 3% of rated terminal voltage. Means the full load armature voltage drop. In the armature, the voltage drop is nothing but what? 3% of rated terminal voltage. It's something about 3% of your rated terminal voltage. That you have to calculate. So IA into RA. So 3%. 3% means what? 0.03 into rated terminal voltage into 220. Then what you get here, EG 226.6. So EJ, now what you calculated, you have calculated EG. Still, what I have to calculate? I have to calculate IA. What is IA here? IA is equal to IL plus ISH. IL plus ISH. So let us calculate now IL. Full load current IL. Full load current IL is nothing but what? The power divided by voltage. You know the output power of the machine, 50 kilowatt. 50 kilowatt divided by the voltage, 220. What you got here? 227 ampere. That is full load current. And you calculate what? Calculate the shunt field current. Shunt field current ISH. You can see here in the problem it has given the data. Okay. The field current is what? 1% of the rated full load current. Means the field current. Field current is 1% of rated full load current. Okay. Whatever the ISH is something but the 1% of rated full load current. In this expression, you have calculated what? We have calculated IL. So IL is equal to 50 into nothing but power divided by 220 watt, 227 amperes. So calculate a shunt field current. It's nothing but what? 1%. 1% of the rated full load current. So 0.01 into 227. So what we got here? 0.01 into 227 is equal to what? 2.27 amperes. Once you got IL and ISH, always you can calculate what? Always you can calculate armature current. So armature current IA is equal to what? IL plus ISH, 227 plus 2.27. What you get? 229.27 amperes. Once you got IA and EG, then you can calculate what? Power developed by the armature. Power developed by the armature, P is equal to what? EG into IA. So EG you got 226.6 into 229.27. What you got? 51.95 kilowatt. You can see here power developed by the armature include what? Include other losses also, because the output of the machine is you got 50 kilowatt. Here the power developed by the armature, what you got? 51.95. The remaining 1.95 definitely will be a losses. Okay. Now here in the problem, it is given say is equal to polar by pole pitch, B by tau is equal to 0.67. You can see here in the problem, the polar to pole pitch is given by what? Is given by 0.67. Okay, 0.67. Next, output coefficient. Output coefficient C naught is equal to what? Phi square. Say here in earlier in the previous problem, output equation C naught is equal to you can put it C naught is equal to okay, phi square BAV into AC. But in this problem, instead of BAV, what it has given? It has given the maximum density. Maximum density means it has given BG is given. Okay, BG is given. So here BG is given. So, okay. Now what is BG? So you can calculate BG is BG is something but what? BG is equal to BAV by psi. That's the formula. BG is equal to BAV by psi. So substitute for BAV. BAV is something but what? BG into psi. I'm saying I repeat, BG is equal to BAV by psi. So substitute for BAV. BAV is nothing but what? BG into psi. So pi square psi into BG into AC into 10 power minus 3. Okay. Because I already discussed in the output equation, if they suppose instead of BAV, it will ask in terms of BG. Okay. B square, pi square psi into BG into AC. Substitute psi is given 0.67. BG is given 0.83 and 30,000 10 power minus 3. What you got the output coefficient here? 165. Then machine speed we calculate, machine speed per second, speed per second. Don't write once again a synchronous speed with respect to AC. In DC, you write speed per second or machine speed per second. Okay, machine speed per second. Machine speed per second n is equal to 600 by 60. So here what is the speed given? Speed is 600 rpm. Convert into second. 600 by 60. What you get? 10 rps. Substitute here. D square L is equal to P divided by C naught into N. 51.95 divided by 165 into 10. So 0.0315 meter cube. This is equation 1. Once again, we have square pole. Core length L by pole R B is equal to 1 for square pole. Psi is equal to B by tau. Core length is equal to pole R B side tau. Psi is given 0.67 to T. T is equal to pi D by P. P is given. P is equal to 4. So what you get here? 0.526 T. Equation 2. Substituting for L from equation 2 to equation 1. So what you can get? You can get D and you can get L. You can get D and L. So If you see in this problem, instead of they're not given efficiency, they are given some losses. Okay, with respect to field losses or with respect to armature losses. Then you have to calculate what you have to calculate the power developed by the armature using this relation. Okay, a very much important problem. Very much important problem. This problem it has been asked for several times. Okay, this is one type of problem. And first problem what you solve, a simple one, that is okay. Then we have one more type of problem. Let us go to one more type of problem. Fourth problem. Once again, it is an important one. Let us see. Okay. Calculate the diameter and length of the armature for a 7.5 kilowatt. This problem is from Ekesani only. This and this, I think. This two problem is from Ekesani. Okay. Calculate the diameter and length of armature for 7.5 kilowatt, 4-pole, 1000 RPM, 220 volt shunt motor. Give full load efficiency of 0.83. Maximum gap flux density is given. Once again, it is given what? Maximum gap flux density. Specific electrical loading, field form factor. Field form factor is nothing but what? Psi. KF. KF is nothing but psi. Because BG is equal to BAV by psi or BAV divided by KF. Both are same. Instead of psi, they may give field form factor. Psi is something but what? Pole pitch by polar by pole pitch, or they may give field form factor. Field form factor is equal to 0.7. Assume that the maximum efficiency occurs at the full load and field current is 2.5% of rated current and pole phase is square. So in this emission, everyone knows when does a maximum efficiency occurs when the constant loss is equal to variable loss. Variable loss are a copper loss. When the constant loss is equal to your copper loss, then the maximum efficiency occurs. Normally, a copper loss or variable loss includes what? Losses in the armature, nothing but A square RA, and even some losses will account in the excitation of your field. There also we have some losses which comes under variable losses, and the pole phase is square. And here what they given? They given the field current is 2.5% the rated current, means field current. Field current here, this field current, whatever the ISH is something about 2.5% the rated current. And regarding armature loss, regarding this one, regarding IA, they are not given. They are not given this loss. Okay, let us see. Now once again, these are the some of the equation. Some of the equation regarding this is motor is not a generator; it is a shunt motor. And these are the some equations regarding the shunt motor. Regarding the shunt motor, everyone knows regarding this equation. You can go through it. Now, what do you have to calculate? Once again, you have to calculate D and L based on the parameters. Given this problem. Now, output P. What is input power? Normally here we can do this problem in you can do the problem in two ways. Two ways you can give the problem. This is one way of doing it. One way of finding out PA. Other way is what? Other ways based on the data given the problem, you can find it out. So I'll tell both the ways of finding out PA. Whichever you feel convenient or easy, you can follow. Okay. See, main thing what I want to calculate. What I want to calculate PA. If I want to calculate PA, then the remaining thing will be simple. If I calculate PA, the remaining thing C0, D square L, and D and L, then that will be easier. So, how to calculate PA? PA means power delivered by the armature. Power delivered by the armature. I'll going to specify in two steps, two different techniques. Whichever, if you want easier, you can follow it. Let us see one step. First technique. Let us see. Now, output power of the motor will be P. Input power is nothing but what? Output power by efficiency. Output power is nothing but P divided by efficiency. Total losses is nothing but what? Input power minus output power. Input power minus output power. Okay. Then you take LCM here. P minus P divided by efficiency is equal to what? Then you take P outside. P is equal to 1 minus efficiency or eta divided by eta efficiency. Okay. Total losses is given by what? P into 1 minus N divided by efficiency. Okay. The friction and windage and iron loss for a small motor may be taken as 1/3 of total losses. Whatever the total losses you're going to calculate, the friction and windage loss, you can take 1/3 of total losses. So 1/3 P into 1 minus eta divided by eta or efficiency. Yes, sir. Yes, the power developed by the armature is equal to what? Is equal to P is equal to P plus friction plus windage and iron loss. Since they are not given regarding the armature current or armature losses, we are taking what? Friction, windage and iron losses. That is nothing but of 1/3. Now, P is equal to P plus friction plus windage plus iron losses. So P plus 1/3 P into 1 minus N divided by efficiency. Just take SCM and you calculate here. Take SCM and you calculate. Then finally what you get here? 2NP to eta efficiency P plus P divided by 3N. Take P outside. 1 plus 2 efficiency divided by 3 into efficiency eta. Then substitute here. What is the rating of the machine given? Rating of the machine P is nothing but 7.5. 1 plus 2 into efficiency is what? Efficiency is given 0.83 divided by 3 into 0.83. So what you get power developed by the armature P is nothing but what? 8.01 kilowatt. This is one way of finding out power developed by the armature for this problem. The other way of finding out, so already I given in the already with respect to this data, you try to calculate. This is one way of finding out. What you have done means you have taken 1/3 of the friction, windage and iron loss will be 1/3 of what? 1/3 of total losses. This will be total losses. And we have taken 1/3 of total losses. Okay. Let us go for one more method. Input power. Input power once again P by N 7.5 divided by 0.83. What you get here? 9.04 kilowatt. Total losses. Input power minus output power. What is the input power now? Input power is nothing but 9.04 minus 7.5. What you get here? 1.53. So total losses will be what? 1.53 kilowatt. So 1.53 kilowatt. Since the maximum efficiency occurs at full load, the constant loss and armature loss. Armature loss is nothing but the variable loss. Losses are equal at full load. Since the maximum efficiency occurs at full load, constant loss is equal to a variable loss. Means both losses will be equal. So try to get the constant loss. Constant loss is equal to what? So 1540 means I have taken in watts. 1540 divided by 2. 770 kilowatt. 770 kilowatt. This is a constant loss. What is the constant loss? It may be rotational loss, it may be series loss, it may be eddy current loss. All those normally if iron loss can be called as a constant loss. So 770 kilowatt. Okay, this is the constant loss because then regarding the variable loss or armature loss, it will be another 770 kilowatt. Okay. That is regarding what? Regarding the remaining armature loss will be what? 770 kilowatt. Okay. Now, let us calculate now. After calculating the constant loss, let us calculate full load motor current or full load. Power by voltage. Into here, what I have to take here, efficiency is given. One more step, efficiency you have to take into consideration. P is something but 7.5 kilowatt into 220 watt into efficiency. So 0.83 full load current. I is equal to P into V into efficiency. What you get here? 41.1. That is your full load. That is your full load current. So full load current I. Okay, full load current I. I think what you are. If you go back to this figure, a full load current. This is something but what? Full load current I. Okay, I. Full load current of your motor is nothing but I. Where I is nothing but what? IA plus ISH. Okay. Next, field current IF is something but what? 2.5%. 2.5% of your full load current. If you go back to the problem, the field current is 2.5% of rated current. 2.5% of rated current. You can take here field current. IF is equal to 2.5% of your rated current. What is the rated current here? Rated current of the motor 41.1. So what will be field current? Field current will be 1.03. So 1.03. So next, field I square R losses. Field means what is the field losses? Field losses I can calculate. Field I square R losses. You can calculate what voltage, whatever the voltage divided by the resistance. R I square R. What are the losses in the field? What is the losses losses in the field? Okay. Since they're not given regarding the voltage here, since this 220 volts input. Okay. Since here you try to calculate what? Try to calculate this I square R loss. Okay. I square R loss can be, say some approximation I've done here. So I square R can be written as I square R loss. This is R, I square can be written what? V by R. So V square by R square. So one R get cancelled, and this V can be written as what? V into V by R. So then what you get here? V into V by R. Once again, V by R can be written as I. So finally, what you can write? V into I. So field I square R losses can be written as what? V into I. 220 volt into 1.03. What is field current here? 1.03 equal to what? 227 watts. Next, friction and windage loss. Friction and windage loss or iron loss. That is called as a constant loss. But regarding here, a little bit I doubt I got here because this I have taken from the A.K. Sani book. A field I square R loss will come under the variable loss or come under the copper loss. But in the book, this step I'll confirm and tell you once again. They are just minus from the friction, windage, and iron loss because the field I square R loss comes under the variable losses, nothing but your copper losses. Okay. They are minus from the friction and windage losses. This step once again I'll tell you. I'll confirm and I'll tell you. 770 minus 227 is nothing but what? 543 watts. Okay. Why they minus this I square R loss with respect to the constant losses? I'll tell you. Okay. I tell this step I'll tell you. Hence, the power developed by the armature P is equal to P plus friction, windage, and iron loss. Since even I got doubt regarding this one, I'll tell you later. Okay. Since they are taken from A.K. Sani, I'll tell you later. P is equal to P plus friction, windage, and iron loss. So what I got here? 7.5 plus 0.543 kilowatt. So what I got here? 8.04 kilowatt. So if you compare the two steps here, by using the data given the problem, what I got here, PA, power delivered by the armature P is equal to what? 8.04 kilowatt. I can calculate this one by using these steps. Otherwise, this one more method I can calculate by using this formula. What I got here, 8.01 kilowatt. Here also what I got, 8.04 kilowatt. Both are same. Either you can go for this method, or either you can go for either you can go for this method. This I'll tell you later. I got some doubt regarding this one. I'll tell you later. So either you can go for this method, or I can go for this method. Once you find out PA, then the remaining will be easier. After finding out power delivered by armature, then use the output coefficient. C naught is equal to, since BG is given, pi square psi BG into AC 10 power minus 3. This you calculate 0.7 into 0.10, that is 10 power minus 3. So what you got here? 196.5. So machine speed you calculate 16.66. D square will you calculate period of C naught into N. 0.026 meter cube. Once again, it is given as square pole phase, core length by pole pitch, L by B is equal to 1. For square pole phase, core length is equal to B, and psi is given. Psi instead of psi is given. Psi is equal to what? Polar by pole pitch, B by tau. Okay. Since here in the problem, they are not given psi. Instead of psi, what they given? They given field form factor. Field form factor Kf is also equal to psi. Okay. Field form factor also equal to psi. So B is equal to psi into tau. The psi can be replaced by what? Field form factor into tau. 0.7 into tau. 0.7 into pi d by P. 0.7 into pi d by 4. You get equation 2. Using equation 2 and 1, you can calculate what? You can calculate D and A. This is what? This is a solution of your force problem. Okay.